Hello everybody and welcome back. This is the lecture where we're going to start talking about data structures, which are basically things that you can create in your program that allow you to store data in a way that is perhaps more efficient for solving certain kinds of problems. We're going to talk about three main data structures in this lecture, and in the process we'll learn about some of the most important data structures that many algorithms use. There's an entire course on data structures in your computer science program, and as a result, you'll learn some more. One of the notable ones that we don't cover are hash tables. There are lots of different kinds of trees. We're just covering one kind of those trees. So there's quite a bit more that you'll need to learn, but this is a really good start to give you kind of a broad overview of some of the most important data structures, and it'll give you a good start. It's really good practice to implement some of these data structures if you're able. Some of the built-in data structures in Python already handle two of the data structures without really doing a whole lot more. But you can also implement them in the way that we're going to suggest. We're going to talk about in this class, which would be to implement it yourself and not rely on the built-in implementation of it. So we'll talk about some basic data structures, especially stacks and queues, and we'll talk about two ways that we can implement each of these two data structures. And then we'll talk about trees, especially binary trees, and in particular a certain ordering of a binary tree called a binary search tree. We'll talk about how insert and delete work in this binary search tree, as well as how to find elements within the binary search tree. So let's jump into it. So first, let's talk about stacks. Stacks is something that we already have a little bit of experience with because I talked about stacks when we were talking about functions. And understanding the stack, because there is a calling stack whenever you're calling functions, will help you understand how functions are called, how recursion works, etc. But stacks are useful in other contexts. We typically will use a stack when we want to do something that we want to reverse, or if we want to put something on the stack to handle later and we're not ready yet to deal with it, we can use a stack where we typically want to do things in a reverse order, and we can use a queue if we want to handle something later. We want to keep things in the same order. So a stack is an example of the first in, last out, or last in, first out, I guess, and that simply means that every time I put something onto the stack, when I ask for something to be taken off of the stack, the very last thing that I added to the stack is the thing that comes off. We're going to talk about an analogy that'll help you understand how the stacks work. Anyway, so it's a LIFO, last in, first out. I like to imagine that there's a really heavy stack of things, and I think I mentioned this in the previous lecture. So it's not possible for me to hold two items from the stack at once. I'm not strong enough to do that. And as a result, when I put something onto the stack, I can't move another item out of the way in order to stick that item underneath some other item. So the only way that I can place something on the stack is on the top. And similarly, when I'm trying to remove something from the stack, I can't remove the second element from the stack because that would mean I have to hold the top element and then grab the second element from underneath it. I can't do that. I can only lift one element at a time, so I can only take the element that's at the top of the stack. So we have two operations that are very closely related to that. Push, which is just stack terminology for putting an item on the stack, but specifically we put it on the top of the stack, and pop, which removes the element at the top of the stack. We can also peek at the top of the stack, so this is going to see what the item is at the top of the stack, but it's going to leave it on the stack, whereas pop will also remove it. So usually the pop function will return the top value, but will also remove it from the stack. And the top function will also return the top value, but it won't remove it from the stack. Usually push doesn't return anything, it just takes the new element to be pushed onto the stack. There's usually also a function that determines whether or not the stack is empty. I really should make this in snake case, so I realize now that I didn't do that, so I apologize about that. So this should be is underscore empty, perhaps. But anyway. So here's some example code about how to use Python lists as a stack, because this is sort of built-in behavior that already exists. So for instance, when I create a new list, That's kind of like instantiating a new stack. So in this first line of code here, I'm just creating a variable called stack, and I'm initializing that to an empty list. And then what I'm going to do is I'm going to use append in order to insert the values at the end of the stack. So this is equivalent to our push function. They don't call it push in lists because if Python called it push, it might get a little bit confused because you can use lists for multiple purposes. In fact, we're going to see that you can use a list as a queue as well. So we don't usually want to mix up the language. But for some reason, actually, they do use the name pop for one of their functions, as we'll see. So we can use append. And if you remember what append does, it adds an element to the end of the stack. So if you're looking at the list from left to right, it'll add it to the right-hand side of the stack. So the first append here is going to add the 1 because it's the only element on the stack. It's both the left side and the right side. But then we append the 2 that gets added to the right of the 1. And then we append the 3 that gets added to the right of the 2. So from left to right, the values are going to be 1, 2, 3. And if we want to see what the element is on the top of the stack, because we're considering the right-hand side of the list to be the top of the stack, then we can actually use stack square bracket -1. And we've talked about this in a previous lecture where if you use an index of -1, that gives you the last element. And so there's no top function, but there's a built-in operator that allows us to do this. There isn't a function that allows us to check to see if the stack is empty, but because it's just a list, we could just check the length of the list, and if it's 0, it's empty. There is actually a function on the stack class called pop, and what it does is it removes by default the thing on the right-hand side or at the end of the list. If you don't pass it any argument at all, it removes the element at the end or the last element of the list. So if you do pop 3, it'll try to remove the value at index 3. And if you say pop 0, it'll try to remove the value at index 0, which is the left side of the stack. But if you don't pass an argument, then it tries to remove the value on the right-hand side of the stack. So that's what we're using here, because pop without any arguments takes the element on the right side, and the right side is what we're using as the top of the stack in our case. And it's a little confusing because normally stacks, when we conceptually observe the stack, we look at it from bottom up. But usually when we show a list, we usually show a list from left to right. So that's why I'm using left to right terminology here. So what if we want to implement our own stack? So obviously, if you're going to go out in industry and work on a job for your employer, you'll probably use the built-in functionality. It already exists. Why wouldn't you use it? But if you wanted to implement your own, there's one advantage to that. You can actually customize how to implement it to make it efficient for whatever your purposes are. And this is built in, so I actually don't know how efficient these functions are. So if I'm doing really big things with a stack with millions of elements, for example, I don't know what the consequences are going to be computationally. So if I end up finding that the built-in behavior for the stack is inadequate, I would write my own with a mind to try to make sure that the operations that I'm going to perform most often are the most efficient operations. So there are two ways that we can implement it if we want to implement it ourselves. And this is meant more generically, not specific to Python, but we could use arrays or we could use a linked list. So Python doesn't have arrays exactly. You can import an array data type using the NumPy library if you want to. But you could also use built-in lists in order to do this. We've kind of already seen that the list has functions that are very stack-like already. But we could just use a list as just a bunch of adjacent values, and that wouldn't be too complicated. So we could still use Python lists to implement this. Whenever I'm saying an array implementation, you should know that in Python we could use Python lists as well. But arrays could be used in a programming language like C++. So basically what you do for the array is you create an array and you put the values at the top. And so the top of the array, or the first index of the array, index 0, that's where we're going to have the bottom element of the stack. And then what we're going to do is going to be an upside down stack. We're going to add the elements just below the previously added element. And instead of growing from the bottom of the array, which is a little bit uncommon, we're going to grow from the top of the array because we usually start at the beginning of the array, so that sort of makes sense. Another way to implement is to use a linked list. Now, we haven't really looked at linked lists just yet, but it is a very commonly used data structure. There are some huge advantages to linked lists, and we're going to talk about a little bit later, and some significant disadvantages to linked lists as well. That's why I'm showing you both of these, because in certain situations, arrays might be the best way to implement the stack, and in other situations, a linked list might be the best way. There isn't a universal best way to implement a stack. And there are more than just these two ways to implement a stack, but these are two of the most common ways to implement a stack and two of the simplest as well. So with a linked list, what happens is you create a node class, and the node class has at least two elements. Sometimes they have more, but the two elements that are in the node class in this case are the value itself, whatever values I'm putting onto the stack. So if it's a stack of strings, for example, the value will be a string. If it's a stack of integers, the value will be an integer. More realistically, it might be something more complicated, like a function call, for instance, if I was representing the calling stack, which might include things like all the arguments and stuff to that function. We've talked about that before. Those would be the values. And then we would have a pointer to the next node. And so with a linked list, all the nodes are in different spaces in memory, and they can be really jumbled up. There's no specific order to them. Wherever there happens to be space, we can just create a new node in that location in memory. And because we're using a pointer to the next node, the next value can be anywhere. And the pointer will just point to another node. So that'll also have a value, and it'll also have a next pointer. So we can have this sequence of values. So similar to the array, with the array we had an integer variable that stored the index of the next available space. That was the top of the stack. A linked list will also have a top as well. It's going to be a pointer in this case. It's going to point to where the last inserted element is. Remember that the last inserted element is inserted at the top. So whatever the last one is, that's the top of the stack. So we have a pointer pointing to that node called top. Okay. So I'm going to show you some animations as well on how these are implemented. We'll talk about conceptually how stacks grow and shrink with the push and pop, but we'll also talk about the array and the linked list implementation. But first of all, let's discuss why we might not want to use arrays. So I want you to think about this. Maybe pause the video and think about what you think the disadvantage might be. If you don't think of anything, maybe watch the videos and see if you can get an idea and a clue from that. And if you can't think of anything, it's fine. Obviously, I'm going to tell you what the disadvantage is, so it's okay. But it does actually help with your learning to take a guess, even if you're wrong, and sometimes especially if you're wrong. It does actually help your learning because you're sort of making, you're putting yourself on the line, and actually there are consequences in your brain if you end up getting it wrong, where you're a lot more open to new ideas. And so that open-mindedness is very advantageous, and you can take advantage of it if you actually, participate in these discussions as much as you can on a recording, obviously. So I'll tell you what the key disadvantage is to using arrays. One disadvantage of using an array is how big should I make the array? Like, how big is the stack going to be? I have to have one array element for every stack value I'm going to have when the stack is at its biggest size. So think about something like a calling stack. The size of the calling stack needs to be at least as big as the number of currently called functions. So for example, I have like a recursive function, and the recursive function has 8 recursive calls. I need to have at least 8 elements in my array. And back when we were talking about recursion, I showed you some examples which were using infinite recursion. And in that case, obviously, the stack can't be infinite in size. So imagine that Python used an array or used Python lists or whatever to keep track of the calling of the various functions. And in the infinite recursion example, It ran out when the array ran out of space. And that's why Python said, oh, you've reached the recursion depth limit of 100 or whatever it is. So that's the main disadvantage. And just related to that is I might decide to make the array really big just to make sure that I have enough room in my array so that I can solve all the common problems, because maybe having something like 50 function calls isn't actually abnormal. That might be a perfectly normal program just doing its normal behavior. So I need to make sure that it's at least 50, right? So I might make the array extra large, and kind of a side disadvantage to that is that I'm going to have this big array all the time that most of the time I'm not going to use, because it has to be as big as possible to store all the perfectly legitimate values, even if those situations are rare. So maybe I very rarely use 100 calls in my calling stack, but I make my array 100 anyway. I have a lot of wasted space as a result of making the array that big. So arrays, by their nature, so lists in Python are actually dynamic. We can make them grow and shrink. But arrays, like arrays in C++ or arrays in Java, they are not. They're very static. We declare them to be a certain size. And if we run out of space, the only way to resize an array is to create a whole new array that's bigger, let's say, and then copy all the values from the old array to the new array and then delete the old array. And that's very computationally expensive. So I don't want to be doing that very often. So often what will happen with arrays is we make sure that the array is plenty big enough so we don't have to do that, except in really extreme situations. And as a result, that's going to mean that we can have our arrays be really big. But it's going to waste a lot of space having them be big all the time, and we're not going to use that size most of the time. All right, before we start talking about the linked list implementation, I want to start talking about pointers. Now, some of you are taking a course where you're dealing with a programming language like C++ that supports pointers. And so you probably already have an understanding of pointers. But if you're like most students, even students who have taken a course about pointers still have some things that they don't quite fully understand about them. So I just want to kind of go over some of the most important points that you should know about pointers if you're going to work with them. And the reason why I'm doing this is because linked lists need pointers. Every single node has a pointer to the next node in the chain. So remember that a pointer is just a variable that stores an integer, so it's not really that different than an integer variable, except that the integer's purpose is to be an address in memory where some other value is stored. So a pointer's value is the address. And at that pointer location in memory, there's probably some other value. It can be confusing for students sometimes when they're using pointers, what's in the pointer. Especially a lot of times, I might create, for example, an object such as machine, let's say. I create an object, an instance of machine, and it's somewhere in memory, and I create a pointer to it, and the pointer's name is maybe machine pointer or something like that. So in my head, I might think that this machine pointer variable contains a machine, but it really doesn't. It contains the address of where in memory the data for that machine is located. So a pointer isn't a complicated thing. It really is just an integer variable, but it stores an address in memory. Some of the things, though, that make it take a while to learn pointers is that we have to make sure of a few things. Number one, if I have a memory address in my pointer variable, I have to make sure that it's a valid address. And the most common culprit is I have a pointer that's set to null. In many programming languages, null is just 0. And 0 is an address in memory, but it's not an address that your program probably has access to. So I'm going to call this an invalid address. So I can give you a rough idea of how memory works, but obviously not a complete picture. Whenever an application runs in your operating system, that application sets aside some memory for your application. And there's a bunch of other applications also running on your computer. Each of those applications has their own memory space, and their memory space is protected. So when program A is running, program B is not able to see the contents of memory that's owned by program A. And so they're not able to see each other's information. And that's really important, because if I have a program that ends up getting compromised. Let's say I have a web browser and I navigate to some shady website and there's some malicious code on there. One good thing about it is that it can only affect the areas of memory that had to do with that one browser tab that I was doing. And all of my other applications all have their own memory space and it's protected. And this process is called memory segmentation. And it's pretty common, in fact, when you try to access a memory address that's invalid, or it's a valid memory address, but you are not, your program is not the owner of that memory address. In that case, then, you will get a segmentation fault because the address you're trying to access, that memory is not yours, so you don't have permission to access it. So it'll give you a segmentation fault, which is the operating system's way of complaining when you try to access something that you don't have the ability to access. Because pointers are actually a little bit challenging to learn, they do take some time. You're going to have to give yourself a couple of weeks and do a lot of practicing in order to be basically a professional pointer programmer. There are a lot of programming languages like Python and Java and JavaScript that don't even have pointers at all. So programming languages like C and C++ have them, but many programming languages do not. Python's in the list of programming languages that don't have pointers, but they actually do have something that's very similar to a pointer called a reference. And Java has references, and C# has references, and JavaScript has references. They serve the same purpose as a pointer. A reference is a variable that stores a memory location, and if you go to that memory location, that's where some value is. But the key difference between pointers and references is that if you have a pointer, you can do pointer arithmetic with that pointer variable. So for example, if I had a pointer that points to the first element of an integer array, I could add some value to the address. Maybe I'll add 4 to it if each of the integers in the array is 32 bits in size, because 8 bits is one position. I can add 4 to that pointer to make the pointer, instead of pointing to the first element in the array, it now points to the second element of the array. And you can do pointer arithmetic in programming languages that support pointers because they're really just storing integer values, and I can increase an integer value by 4. References don't work that way at all. In Python, I can have a variable that stores the memory address of where some value is, but I can't change that address in any way. I can set it to point to a different object, but I can't actually just add mathematically to the address and then point to some other area in memory. And that difference is significant because just being able to point to different objects makes references very easy, but being able to do pointer arithmetic means that we could end up with an address that I don't have access to because I can add or subtract values to it that makes the memory address now point to some other program's memory, or it points to an invalid address like -2. You can't have a negative address. Or it happens to point to somewhere in the middle of an integer value. So that's one of the points that's made here. The memory address lines up with the start of a value. If a value takes up more than one memory space, I could end up referencing an address that's somewhere in the middle of that value, which obviously is going to give me some value that's incorrect. So pointers have some complexities to them, and we can use both pointers and references to implement a linked list. So if you use a programming language like Python, you can implement linked lists without too much trouble. There's not really a whole lot that could go wrong. But if you're using a programming language like C and C++, you'll have to take extra precautions and make sure that you're following the correct procedures for doing pointers as instructed by whoever is teaching you about pointers right now. Okay, so when you're using a linked list to implement a stack, there are some advantages and disadvantages. And if we think about the disadvantage of arrays, that we have to kind of predetermine the size of the array. With a linked list, that's not true. So I would say that an advantage of a linked list is that it can grow and shrink as much as we may need. If I need more elements in my linked list, I just create another node, and then I point one of the next pointers to that new node. So now it's a part of the chain. And I can add as many of those linked list nodes as I want. So the linked list can grow and shrink as I need it. And I can free up memory by deleting nodes, and I can make my linked list longer by allocating some more memory to create some new nodes. So it's actually really nice. It's a very dynamic sort of list. And in fact, you end up with something that's similar to Python lists, where Python lists are also quite dynamic. We can add and remove things from a list quite easily, whereas you can't really do that with an array. An array is usually a static size. So that's a good thing, I would say, and a huge advantage of a linked list. There is a small disadvantage of a linked list in that it adds some complexity to it, especially if you're using a programming language with pointers, because, as I said, pointers are prone to errors, especially for people who are not super familiar with how to program using pointers. But the biggest disadvantage of using linked lists is that the nodes themselves have some overhead. And so every time I add a new element to, so for example, if I have an array and the values in the array are just integers, imagine I have 100 elements in my array and I want to store 100 values. Well, an array only takes up 100 times whatever the size of the value is. So if it's 100 integers, and integers take up 4 bytes, then it's going to take up 400 bytes. There's no overhead. Each of the array elements are literally right adjacent to each other. So it's just an integer, and right next to that integer, the next integer. But a linked list has that extra overhead. I mentioned that when you create a linked list element, the node, it has the value and also a next pointer. So if you think about a linked list of integers, then I have to have space for the integer in each of the nodes, but I also have to have space for the pointer in each of the nodes. And strangely enough, on a 64-bit computer, an integer will take 4 bytes, and a pointer will actually take up 8 bytes. So the pointer is actually bigger than the value I'm trying to store there. So if I want to store 100 integers using a linked list, it's actually going to take 1,200 bytes, whereas an array of integers would only take 400 bytes. So it takes a lot of extra space in order to create a linked list of a certain size. The advantage, of course, so that's an advantage of arrays, that they don't have any of that extra overhead. But the advantage of the linked list means that that's only in the worst case. So in the worst case, I have a completely maximum stack, and I want to have 100 elements at maximum in my stack. And in that case, I need to have 1,200 bytes. But if most of the time, the stack only has 5 or 6 elements in it, that's going to be much smaller than the array of 100 elements that I had to create to match the maximum demands. Because the linked list can shrink when I don't need it, it means that I free up memory for other purposes. So anyway, you can see that both have kind of their advantages and disadvantages, and they both center around how much memory I'm using. But nevertheless, it's a pretty straightforward process. Both of them are actually quite efficient. So we're going to see how they're implemented, and it's done in a very efficient way. So in this example, we have some simple code which is going to show how we can add and remove elements from a stack. So let's watch this code execute. So the stack is initially empty on the right-hand side. First thing we're going to do is push a new element 7 onto the stack. Because you can only put elements onto the top of the stack, 7 gets put onto the top of the stack, which is also the bottom of the stack because the stack happens to be empty. Next, we're going to push -3 onto the stack. This guy again goes onto the top of the stack. 7 is still at the bottom. Then we push a 1 onto the stack. There isn't anywhere else I can put the 1 except for on top of the stack. Remember, that's what makes the stack so easy conceptually to understand, is you can only add new elements to the top of the stack, and you can only remove elements from the top of the stack. So that being said, let's move on to where we remove our first element. So stack.pop, in this case, is going to remove the 1 because it's the element at the top of the stack. Then we push an 8, which goes onto the top of the stack, replacing the 1. And then we pop, which is going to pop the 8. And we pop again. This time that'll pop the -3. And finally we pop one more time, which pops the 7. So one way to implement a stack is to do so using an array. So you can see here we have an empty array on the right-hand side and the exact same code for the stack on the left-hand side. And we'll see what happens when we start to add and remove elements from the stack using an array. So the array indexes are shown here. We have a label called top index, which is going to keep track of the index where we're going to insert the next value. Remember, when you put values onto a stack, you put it into the top. So the top index will point to the location where we're going to insert the next value. So the first line of code is going to insert a 7 to the top of the stack, and that 7 is going to move into position 0 because that's where the top index points. So you can see the 7 gets inserted in the first position. We also increment the top index because next time we insert a value, the top of the stack is now at index 1. It's a little bit weird because I'm usually showing arrays using 0 at the top, and as a result, the array goes down, and so we usually talk about a stack growing up, but we'll have to picture this stack upside down because this is the normal way to visualize an array. So pushing the -3, we put it at the location 1 rather, and for top index gets increased to 2, and then we put the 1 at the new position top index. We increase top index again, and now when we pop, what we're going to do is we're going to decrease top index, and we're going to delete the value at that location, and that's the value, that 1 in this case, that's going to be popped off the stack. Normally the pop function returns the value that gets deleted, that way it doesn't disappear completely. We can use it for something. Okay, so we are going to decrease the top index and remove that value. We push an 8, we're going to push it at index 2 because that's the top. And then we pop the value, we're going to decrease the top index and delete the 8. We pop again, we're going to decrease the top index and delete the -3. And we pop again, we're going to decrease the top index and delete the 7. So another way to implement a stack is to use a linked list. I'm going to show the linked list horizontally because, again, that's the way that linked lists are normally represented graphically. So we're going to show that up at the top. But the code for the stack is exactly the same. So functionally, this should be the exact same stack, the same behavior, but it's going to be implemented quite differently. A linked list is a way for you to implement a sequence of data where each element is in a node that has a link to the next one. So you usually use a class. The class might have 2 instance variables, one for the value. So for example, we push the 7 on the stack, the 7 will be the value, and then a pointer to the next node. So each node will have a value and a pointer to the next node. And we're going to implement the stack using this structure. So we're going to have a top again. And while this isn't a top index exactly, this is more like a top pointer. And so even though Python doesn't have pointers and we're using Python in this class, Python does have something very similar to pointers called a reference. And if you think about what a pointer and a reference are, they really just are variables that store an address, a memory address. So this top index here is just the address of where that 7 is located. Where is that structure that contains the 7 and the next pointer? So we create a new node here. We put the 7 in for the value. The next pointer is actually set to null. So null is just a placeholder saying that we don't have a valid address. And that makes sense in this case because the 7 doesn't have a next element to point to. So we actually leave that next pointer null on purpose. All right, the next thing we're going to do is remember this pointer points to the top of the stack. So when we insert the next value, -3, we're going to insert it at the beginning at the top of the stack, and the 7 is going to get shifted to the second from the top element. So you actually see that the 7 gets shifted over, and now the top index is pointed to the new -3 node that we've created. You'll also notice that we do set the next pointer of the -3 node that we just created because it needs to point to the value that was already on the stack before. The old top of the stack is now not the top of the stack anymore, but it's still on the stack, so we need a pointer to it. So the -3 node has a next pointer that points to the 7 node. And we're going to insert another one, a 1, so we're going to shift the -3 over. It's important to note that nothing actually gets shifted in memory. The -3 node and the 7 node actually exist in the same place in memory they always have. But visually, I'm just moving it over to make room because the 1 is at the top of the stack and will represent the top of the stack on the left. Again, I know it's not the top of the stack. We have the array stack is upside down and the linked list stack is kind of on its side. That's just because arrays are usually represented with the smallest index at the top, and linked lists are usually represented with the first value, and the first element of the linked list is on the left-hand side. So I'm just being consistent with that notation. And I'm shifting the -3 and the -7 just for conceptual understanding of how the linked list looks, so that we can just see it in a nice straight line. But in reality, it's even possible that the one node that gets created is somewhere later or earlier in memory. They could be all jumbled up. And so we shouldn't expect there to be any inherent ordering to these values in memory. The ordering comes from the fact that we have this chain of pointers from top index to the one node. Let me actually show the one node being created here. From the top index to the one node, which then points to the -3 node, which then points to the 7 node, and then the 7 node having a null next pointer is an indicator that the 7 node is the last one in this linked list. So this is the order just carried out by these pointers, and the pointers can point up or down in memory, it doesn't matter. All right, now when we do a pop, again, because pop removes the element at the top of the stack, really what we're going to do is we're going to remove the one node, and we're going to make the top index bypass the one node and point to the -3 node. So we'll see how that works. Again, I'm shifting the values just for clarity, but obviously these values don't actually move around in memory. So we delete the -1 value, and we repoint the top index pointer to the -3 node. Then we're going to push an 8, so I'm going to, just for simplicity, I'm going to scooch the other values over, make a new node for the 8, and point that to the old top of the stack, -3. And then when we pop, we're going to pop the 8 node. That's going to delete the 8 node and point the top index to the -3 node. The next pop is going to delete the -3 node and point the top index to the 7 node. And the final pop is going to delete the 7 node and change the top index to null, indicating that there isn't any element on the stack whatsoever. All right, so now let's talk about the next data structure, another one of the simple data structures called a queue. And in many ways, a queue is just the opposite of a stack. So a stack was a last in, first out, or LIFO. Sometimes people say LIFO for the acronym. A queue is just a first in, first out. And if you're British, I guess you have a bit of an advantage, because the British people use the word queue to refer to getting in line for something, getting in line at the coffee shop, for instance. And that's a pretty common thing that we in Canada are quite familiar with. You can't jump to the front of the queue when you're going to the coffee shop, and you have to go to the back of the queue. So whenever you join the queue, when a new element gets added to a queue, it adds it to the back. And then when the coffee shop employee is ready to take your order, they take the order of the person that's at the front of the queue. And first in, first out gives a clue about how that works. The first person to enter the queue is the first person to place their order. And so a queue is usually used when we want to preserve the order and keep it the same, whereas a stack kind of reverses the order, as you've seen through the examples. So a queue will maintain the same ordering. If I want the thing that I found first to be handled first, I would put it in a queue. It's also a very fun word to type out, because it's QUE, UES. And so anyway, that's I like that. Some of the terminology for queue also comes from British English, and so when we talk about entering a queue, that's called enqueuing. And when we remove ourselves from the queue, like we get served by the coffee shop employee, then we dequeue. All right, so enqueue and dequeue. So enqueue is adding an element to the back of the queue, and dequeue is removing an element from the front of the queue. And of course, just like the pop function does, dequeue will also return the value that it finds at the front. There's also a front function which just peeks at the front of the queue and looks at the front element without removing it. And then we might also have a function called isEmpty. So ideally, if we're implementing our own queue, we'd implement at least these 4 functions. Just like though with stacks, there actually is already a way to implement queues just using Python lists, so we don't have to write anything ourselves. So every one of these operations is just one line of code already. And so here's some example code. It's almost identical to the code that we saw for the stack. So you got to pay attention to some of the differences. Obviously, I called the variable q instead of stack, but that doesn't functionally change anything. But you'll notice that we're adding elements to the end of the list here. So we're still appending the 1, 2, and 3 to the end of the list. So in fact, the queue will look exactly the same as the stack from the sample code up until this point. And if we want to look at the front element, well, here's the thing. The front element is actually not on the right-hand side. And with the stack, the top was always on the right-hand side of the list. And that's the back of the queue. The front of the queue is the left-hand side. So I can look at the front of the queue by looking at Q0, and I can look at the back of the queue by looking at Q-1. I can also check to see if it's empty by counting the number of elements in the queue, just like I did with the stack. And here's the key difference. Instead of just calling q.pop with no arguments, which removes the element on the right-hand side of the list, the last element of the list, that's an element at the back, which is not what I want to do with the queue. The coffee shop employee doesn't ask the person at the back of the line for their order. They ask the person at the front of the line. So I actually want to remove the first element from the queue because that's where the front is. So we pass 0 to pop here because I'm saying I want to pop the element at index 0. And now that that element is gone, this, by the way, removes the 1. Now the 2 is at the front of the list. So the next time I call pop 0, it's going to remove the 2 because that's at index 0 now. And now that the 2 is gone, 3 is now at index 0. So the next time I call pop 0, it's going to return 3 because 3, of course, is now at the front at index 0. And then once I delete the 3, there is no value at index 0 because the list is empty. So this is a really easy way to use queues. And again, if you're out in industry, this is what you would use. You wouldn't reinvent the wheel most of the time unless you had a very specific performance characteristics that you needed, in which case you might decide, hey, I want to write my own queue. How would I do that? Well, let's talk about that. And by the way, there are some programming languages that don't have built-in stacks and queues. So this is also important information if you're using a different programming language. And you might want to do it for optimization purposes or because you don't actually have an option already. So not too surprisingly, we can implement queues in the same way that we could implement stacks. So we can implement using an array. And again, I'm talking more like C or C++ style arrays or arrays in Java. Arrays that are static. They can't change their size. They don't grow and shrink. But functionally, we could use a Python list for this. It's just that Python lists can grow and shrink, and so some of the behavior is a little different, and some of the performance would be quite different. An array here, if we're going to analyze the performance of our implementation using an array, it's quite easy to do because we know exactly how things are added and removed from an array. It's quite efficient to add elements to an array, remove elements to an array. As long as there's an empty space in the array, we can add a new value to it. And we can always delete values that are in that array. We just end up making an empty space. So the array is kind of predetermined size. So the array implementation is going to work by creating an array. We have to create the array to be big enough to store the largest size queue that we might want. That's kind of the same issue that we had with a stack. And we'll address this deficiency in a little bit. And we might need to have 2 integer variables, one to point to the back of it'll have the back index, and then we also might have another index called front, and each of these indexes are going to point to different parts of the array where the front element or the back element is located. And the linked list implementation is going to work very similar to the way that the stack linked list worked. We're going to create a node that has 2 components, a value and a pointer to the next node. That's exactly the same as the way we implemented the stack using a linked list. But we're also going to have a pointer that's going to point to the node that's at the front of the queue, called front. And we're also going to have a pointer back, which is a pointer pointing to the address of where the node is at the back of the queue. And some, obviously, details will be seen when we look through how the operations work in each of these implementations. So let's talk about some of the disadvantages. Well, they're not actually that different, really. The disadvantages of using arrays to implement a queue are essentially the same as the disadvantages of using arrays to implement a stack. We have to make sure that the array is big enough to accommodate the biggest queue that we're going to see. And if most of the time our queue is going to be very small, but sometimes we're going to need a really big queue. So imagine, for example, I have a queue to represent some of the processes, some of the jobs that need to execute in my computer. I might have up to 1,000 or 1,000,000 or 1,000,000,000 jobs. So I need to make sure that the array has at least 1,000 or 1,000,000 or 1,000,000,000 elements to accommodate this maximum size. Even if, if I'm just sitting around on my computer watching a YouTube video, there's only going to be something like 30 or 40 jobs, and having a 1,000,000 element array is a huge waste. So that's a big disadvantage here. All right. So for the linked list implementation, we're going to have to use pointers. And when we have arrays, when we implement it using arrays, we have a front pointer and a back pointer. And as we start adding things to the back of the queue and removing things from the front of the queue, both of the pointers tend to shift to the right through the array. And if that keeps happening, obviously, it's going to go off, like the array only has so many positions, right? So eventually we're going to run out of space. So we could make the array bigger so that this will happen much later, but given enough time, we can actually keep adding and enqueuing and dequeuing values from the queue. Eventually these pointers will exceed the boundaries of the array. So we don't obviously want to do that. But there is a pretty easy solution. It's called a circular queue. And basically what happens is we're going to let the pointers wrap around the beginning. So if, for example, we're going to add a new element to our queue, but the array doesn't have any more spaces, we're at the last space already, we can put the next value at the beginning of the queue, and we can just set the new back pointer to the beginning of the queue so that we start adding values on the other side. It's a little hard to picture, but you can kind of imagine that the array is being treated like a ring instead of just a flat array. All right, so the disadvantage of using linked lists to implement a queue is the same disadvantage as using linked lists to implement a stack. Every single time I add a new value, I mean, obviously the huge advantage is that the linked list can grow and shrink. I just create another node. But the problem is, for every single one of those nodes, I need the value that I'm adding to the linked list, and I also need the next pointer. If I'm storing really big values, this is something I didn't mention when we were talking about stacks. If I'm storing really big values, so for example, a stack frame, for instance, the stack frame is huge, and the next pointer is kind of small in comparison to that. So in that case, this overhead is kind of irrelevant. So I wouldn't consider this a huge disadvantage. It really is only a big disadvantage if we're storing really small values in our linked list. And so depending on the type of queue that I want, as I said before, a common use for a queue is to use for processes that have to execute on your CPU. But you only have so many CPU cores that can execute things, so you might put all of those processes in a queue. And then when the CPU becomes available, we grab the process at the front of the queue and we give it some execution time in the CPU. And that's how we give all the processes on our computer a turn to execute a little bit in the CPU over time. And they get these little time slices where they execute a little bit and then they pause for a little bit and some other process executes for a while. And that's the way we can have 30 applications running. Even though I only have 8 cores in my CPU, it's okay for me to run simultaneously 30 processes because everybody gets a turn. And so it kind of cycles through. So that's a common use for a queue. And if you imagine all the information that I would store about a process, including all of its open files, what kinds of what memory does it have access to? Remember I mentioned before, each process has its own memory space that it owns. The operating system's keeping track of all of that stuff, so there's a lot of information about each process. If I'm storing all of that in my linked list, then each linked list node is going to be huge, and the next pointer is going to be very small. So maybe this is pretty insignificant. But it could be if the values that I'm storing are quite small. It could be significant. So this code is quite similar to the code that we had for the stack. And I'm doing that on purpose because I want you to see what the difference is. With a queue, you'll see there's a very different ordering that involves when you put values onto a queue than when you put values onto a stack. And as a result of that, the behavior of the two data structures are quite different. Even though we're inserting the same 4 values or moving them from the stack in the same order, it's ultimately going to result in very different behavior. So you can use a queue in certain situations and a stack in other situations. A stack is really good, for example, for reversing values, because when you put the values onto the stack and you take them off the stack, you get them in the opposite order. A queue, kind of like standing in line, keeps the values in the same order, and that's its biggest advantage. So for example, if you want to remember to do things in the proper order, you can add them to a queue and then pull them off of the queue as you're ready to do those tasks. So for instance, a queue might be used for things like process scheduling, where you want to make sure that the application that tried to run first gets the first crack at the CPU so it can start executing, and the applications that ran later have to wait for that first application to do a little bit of CPU computation. All right, so let's walk through this code. I'm just going to show you it conceptually at first, and I'm going to represent the queue vertically. You can just kind of imagine that we're standing above a line at a coffee shop, and we're watching the people shuffle forward in line. So the first one is NQ. NQ just means to enter the 7 value into the queue. So right now the 7 value is at the front of the queue. The front of the queue is representing at the top here. And then we're going to NQ the -3. And so the -3 is going to get into the back of the queue, which is right behind the 7. And then we're going to NQ a 1. Again, that gets added to the back of the queue, which is behind the -3. Now DQ means to remove something from the queue. And because a queue is first in, first out, that means the element that was added to the queue first is the first one to get DQ'd. So this is quite different from a stack. With a stack, the last element to be added is the first one out, last in, first out. And in this case, if I DQ'd, if I popped a value from the stack, I would get the 1. That was the last thing that was added to the stack. But this is a queue, so the 1 was added last, but the 7 was added first. So we're going to get the 7 first. And just to visually help us represent, when I remove the 7, I'm going to then scooch the -1 and the -3 and the 1 forward to show that they're at the front. All right, then we NQ the 8, that gets added to the back of the queue. Then we DQ, we're going to DQ the front, which is -3. We scooch everything forward. We DQ this time, we're going to DQ the 1 at the front. We scooch the 8 forward, and now we DQ the 8 that's at the front of the queue again. So one way to implement a queue is to use an array, just like with the stack. And so here I've got an empty array. And we're going to walk through the exact same code again, and we'll just see how that gets implemented using an array implementation. Unlike the array implementation of the stack, we're actually going to need 2 indexes, one to point to the front and one to point to the back of the queue. So there's the indexes, there's our front index and our back index. I just put one on one side and one on the other side just to not make it too squished together. First, we're going to NQ the 7. So the 7 is going to get added at the index that front index contains, because we always, back index contains rather. We always NQ, we always enter the queue at the back. You can think of it like when you're going to a coffee shop, you get into the back of the line. And so the back and the front are the same at this point because the queue is empty. So the 7 gets inserted at index 0, which is where back index is. All right, now we're going to NQ the -3 at index 1, because that's, again, where the back index is set. Or notice that we're incrementing back index, but we're not touching the front index. When we NQ the 1, we're going to insert that at back index 2 and increment the back index so that it's equal to 3. And now we're ready to DQ. We're going to DQ from the front because, again, first in, first out. We're going to remove the element that's at the front of the queue first. So we're going to remove the 7, and I'm going to increment the front index. And then I'm going to NQ. That goes at the back, remember? So put the 8 where the back index is and increment the back index. We're going to DQ again. We're going to delete the 3 and increment the front index. Then we're going to delete the 1 and increment the front index. And then we're going to delete the 8 and then increment the front index. All right, so an important point here is that we can tell that this queue is empty because the back index and the front index are equal to each other, just like they were at the beginning. But you'll notice that there's a little bit of a strange thing that's happened as a result of adding and removing these values from this queue, that the back index and the front index have wandered later in the array. They're not at the beginning of the array like they once were. This is actually easily resolved, and you'll learn about the resolution in more detail in a future course about data structures. But for right now, just suffice it to say that the queue will wrap around to the beginning of the array again. So if we kept on adding values past index 5, if index 5 was the last element of this array, we would insert the next value at index 0. And you can see that there's room there now. There's nothing in 0 through 3. They're just not being used anyway. So that's one way to solve that issue. So the other way to implement a queue, and I've just moved all the code down into the bottom right to make some space here. Again, I'm going to use a linked list, and it's going to go along the top from left to right, just in keeping with how linked lists are normally represented. And just like we did with the array, we are going to need two locations remembered. So we're going to have actually two pointers in this case, because linked lists typically use pointers or references. And so we're going to have a back index or a front index, or maybe this would be better named a back pointer and a front pointer. Right now, they're both null because there's nothing in the queue. But when we add the 7, we're going to create a new node that has a 7 in it, and it has a next pointer of null, and both the back index and the front index are going to be pointed to that new node. All right, so obviously the front index is going to keep track of which element was added earliest to the queue. The back index, however, is going to change as we start to add new values to the queue. So let's add the -3 and see that in action. So when we add the -3, we're going to create a node for the -3. We shift the back index so that it now points to that -3 node. We also create a next pointer from the original front element so that we know what the next value in the queue is. So we know the first element in the queue is the 7, and the second element in the queue is a -3. We use the next pointer in order to enforce that ordering. So now we're going to enqueue a 1, so we're going to create a node for that 1. We're going to point the -3 node to it, and we're going to increase the back index. So we're going to move the back index so that it points to the -1. All right, that one a little bit quick. Let me go back a little bit here. For the dequeue, we're going to remove the element at the front index, and we're going to repoint the front index to the next node. And the way we get that is we look at the front node's next pointer. So in this case, take a look at the front node, the 7 node. It has a next pointer which points to -3. So we know the address of where the node that containing the -3 is. So all we need to do is change the front index or the front pointer to point to the -3 node, and then we can delete the 7 node. So that's what we do when we find a dequeue statement. Okay, and I'm just going to shift everything to the left just for consistency. Next thing we're going to do is we're going to enqueue an 8. So we always enqueue at the back. So we're going to insert it after the back node. So the back node right now is the 1, and there's nothing after the 1. It doesn't have a next pointer. So let's create a new node which has an 8, and let's point the next pointer from the 1 node to that new 8 node. And we'll change the back index to point to the new 8 node as well. All right, then we're going to dequeue, and that's going to be the same process we just saw. We're going to delete the -3 node, but before we do that, we're going to move the front index so that it points to the second node following the next pointer of the first node. And then again, we dequeue. So we're going to set the front index to point to the second node by following the next pointer of the first node, and then we can delete the first node. That's the 1 in this case. And then for the final dequeue, again, we are going to change the front index to point to the value that the next node. There isn't a next node in this case, but that actually isn't a big problem, because what we want to do is we want to set front index to the next pointer of the first element of the queue. And you can see in this case that the next pointer of this 8 node is set to null. So by by setting front index to the first element's next pointer, we're going to be setting front index to null, which is actually what we want if we want to have an empty queue. The only special case that we have to handle here is that if we delete the 8, we also need to make sure that we don't have back index pointing to anything. Because with pointers, they're really just variables that contain memory addresses. And even if you delete the thing that's at that memory address, a pointer still has a valid number in it that points to that memory location, even though it doesn't necessarily have that value anymore. And in fact, if you understand how memory works, which you'll learn about a little bit later in your degree, memory might not even be accessible by you anymore. So each application has its own reserve space in memory, and the operating system makes sure that each application doesn't access the memory of any of the other applications. Each process has its own memory permissions. So if I say I don't want this 8 anymore, I'm giving it back to the operating system, and maybe that same location in memory now belongs to some other process that's running on my computer, and I can't access that memory. I'll get some kind of an error. And if you've done any pointer programming, you're probably quite familiar with this. You'll sometimes get an error called the segmentation fault, or a little bit less common is a bus error. That's what you're experiencing in that situation. So it's important for me to write nice and clean code. So I want to make sure to set the front index to null in this case, because the DQ is removing the last element. But also I want to set the back index to null, which isn't going to happen unless I explicitly do it. Okay, so you can see now they're both set to null and the queue is empty again. All right, just related to a priority queue is something called, related to a queue is something called a priority queue. And just like a queue in a stack, it's a general data structure that can be implemented in lots of different ways. But a priority queue is like a queue. And you've probably experienced a priority queue before. If you were to go to the emergency room, let's say, and let's say you injured your finger, okay, and it's a pretty bad injury, but it's not a life-threatening injury. So you go to the emergency room because it's 3 o'clock in the morning and nobody else is open. So you're sitting there in the waiting room in the emergency room, and somebody else is there with exactly the same finger injury, and they got there before you. Because it's a queue, the person that got there before you gets looked at by the doctor first, right? She's going to look at the list and say, oh, we got 2 finger injuries. Who was here first? So that's a normal queue. But then somebody else comes in and they have a really serious, perhaps life-threatening injury, or maybe they're having a heart attack or something like that. So that's really serious, and time is of the essence, and no offense, you and your finger can wait. What's going to happen is the doctor is going to look at that list and jump that heart attack person to the front of the list. And so she's going to look at that heart attack person first before the person with the injured finger. And that's called triage, and it's a pretty normal operation in medical fields, but it happens in a lot of other situations as well. It might even happen in the example we were just talking about with process scheduling on your computer, because I might prefer to execute certain processes more, and they should get first crack. So for example, the operating system probably has priority over all the other applications that are running on the computer. So this is called the priority queue. Basically what it means is it's a queue, except that things are ordered first by their priority, and then second by the order in which they were added. So it's not a true FIFO, first in, first out, because things jump right to the front of the queue if they have the highest priority. And if I have 2 highest priority values, the 2 highest priority values will still be ordered by the order in which they were added to the queue. So if I had 2 heart attack victims come in, the first heart attack victim to come in would be looked at by the doctor first. So there's tons of ways you could implement a priority queue. You could implement it using a sorted array if you wanted to. You could use a sorting algorithm like we've talked about. And in that case, that's pretty easy because it's sorted by priority. And so you could just literally pick the first element of the array, and that would be the one with the highest priority. You could also use a sorted array, an unsorted array, I mean, and what you could do in that case is just add them to the array. So it's really efficient to add things to the array because you just add them to the end, for instance. But then when you want to grab the next value out of the priority queue, you have to search through the array, finding the one that has the highest priority. And so in that case, that might be efficient to add to NQ things and very inefficient to DQ things, whereas the sorted array is going to be very inefficient to NQ things, but DQing things is just a matter of taking the front element of the array. So it should be much more efficient to DQ things in that situation. And so it's a trade-off, right? And so if we're implementing a priority queue, if we use a sorted list, then one operation is fast and the other one is slow. And if we use an unsorted list, it's the other way around. But one of the operations is slow. So there's actually an advanced data structure called a heap, which is designed to implement a priority queue such that adding things to the queue, we call that NQ, and removing it from the queue, we call that DQ, are both efficient. And so heaps are a little bit more advanced data structure. It is a binary tree, so it's related to the data structure we're about to cover next, but it's a little bit more advanced. And so it's introduced, I think, in the data structures course, or perhaps in the third year in the algorithm design analysis course. So one of those two courses you'll learn about heaps. And a thing that you can use heaps for is actually to create another sorting algorithm called heap sort. And then the heap actually works as the data structure that does all the sorting for us in that sort function, which is a very efficient sort. Okay, so let's talk a little bit about trees. So trees are a common data structure in computer science. So far, what we've been talking about are these kind of one-dimensional data structures. They're stacks and queues, and they're very similar to each other, but they're very one-dimensional. Sometimes I might want to store things in a more complicated way so that I can get some additional benefits from it. For example, stacks and queues are great, but the only way that I can get the values are based on the actual ordering that I used. It doesn't help me jump directly to the correct value. Stacks and queues are not designed that way. And so a tree might be designed specifically to help me find values that I'm looking for in as efficient way as possible. So we have talked before about the binary search algorithm, which is when you take a sorted list or a sorted array and you can efficiently search through that array and find the value you're looking for without examining all the elements of the array. You only look at some subset, but the array has to be sorted. A tree can implement something that's in principle basically the same process. Trees are used for all kinds of things though. In whatever your favorite operating system is, for mobile or for your laptop. All your operating systems use trees to represent the file system. They use trees to represent different chunks of memory that you can allocate if one of your programs needs a bit of memory. Trees are used a lot internally in computer programs. So let's talk a little bit about the different types of trees, but it's not going to be an exhaustive review of every kind of tree that we use in CS because there are dozens of them, but we'll talk about a few. So it's a nonlinear data structure, like I mentioned. One variety of tree is called a binary tree, and we've heard the word binary many times. It just simply means two. So a binary tree is a tree where all of the branch nodes have up to 2 children. And I'm going to talk about what a branch node is in a second. Okay, so we can think of a binary tree as being kind of similar to a linked list. A linked list, remember, is a node that has a value and that has a next pointer that points to the next thing. Well, a binary tree is kind of like that, except instead of a next pointer, it has 2 pointers to 2 next nodes. So we might call them the children. So we might have a left child and a right child. And you can have trees that aren't binary. For example, you can have a ternary tree that had 3. It's possible to have other types of trees, or trees that have any number of children if you want them to be, like you would use for a file system, for instance. There's other kinds of trees, but let's focus on the binary tree because it's a very interesting one. And in particular, I want to look at a very specific type of binary tree called a binary search tree. And you might guess from the name that it has something to do with the binary search algorithm. Of course, you'd be right. So in a binary search tree, if you look at the tree, all the values are ordered from left to right. So the smallest values are on the left side and the largest values are on the right side. So there's this inherent left to right ordering in a binary search tree that allows us to do very efficient search using an algorithm that's basically identical to binary search. So it's a tree that very, very efficiently supports binary search, but at the same time, it's very efficient to add and remove values from which a sorted list, a sorted array is not. Okay, so here's an example of a tree, and I just want to show you this so that I can point out some of the terminology that you're used to hearing. A lot of it has to do with the actual trees, real trees in nature, and some of them have more to do with like a family tree. So unfortunately, there's a lot of kind of mixed terminology, which is a little bit confusing, but it's all the standard now, so it's not possible for us to change it. But here we've got ourselves a tree, and I'll just highlight some of the important parts of this tree. So first of all, the top node is called the root node. And it's kind of weird because the root node is at the top of the tree, but I'm no biology expert, but usually trees have the roots down at the bottom. So I guess you can kind of just imagine that this tree is upside down. And at the very top of the tree is the root node, and at the bottom of the tree are the leaves. That's kind of strange. But nevertheless, it is actually helpful in understanding how the terminology typically works. It wouldn't be a problem for us to draw the tree upside down. It's just become commonplace for us to draw the root up at the top. And so it's hard for us computer scientists to change, I guess. Anyway, so that's a root node. Any node that has children is called a branch node. So just, again, a root, trees have roots, and trees have branches. Branches are like the thick part of the tree. And in fact, the root of the tree is also a branch node in this case because it has children. So don't think that a branch or a root, it could be both. So 15 is the root node because it's up at the top, but it's a branch node because it has at least one child. So 15, 9, and 22 are all branch nodes in this case. And everything that's not a branch node is called a leaf node. So everything in a tree is either a branch or a leaf. A leaf node is simply defined as a node that has no children. So a branch node is a node that has at least one child, so therefore mutually exclusive. A leaf node is a node that has no children. And in a binary tree, this is a binary tree, you can see that all the nodes have up to 2 children. We usually say that there is the left child and the right child. So the 15, for example, has a 9 for its left child and a 22 for its right child. Anyway, so leaf, obviously, trees have leaves, trees have branches, trees have roots. This all comes from the plant sort of tree, but we also use terminology that comes from family trees, including the relationship between the nodes. So a branch node's links are called children, okay, which is a little bit strange, but we're not using a tree analogy in this case. But we call it children because you can sort of imagine this is our ancestor. So, for example, I have an ancestor, my grandfather, who came to Canada from Scotland. And so imagine this is my grandfather coming from Scotland. And my grandfather had multiple kids, more than just 2 kids. But he had 11 kids. But imagine that he only had these 2 kids. So maybe my mom and my aunt. Okay, so in this case, these are the children of my grandfather. So this is the left child of my grandfather and the right child of my grandfather. So a real family tree wouldn't use a binary tree because that would mean that people can only have up to 2 children. And in practice, we know that's not generally the case, especially if people of my grandfather's age who typically had 8 or 9 or 12 children. And he had 11 children. And so in this case, we would have to have a node which would support having 11 children or an arbitrary number, really, of children. But this is specifically a binary tree, and so we specifically have 2 separate links, one for the left and one for the right. It just makes it easier for us to conceptualize how the binary tree works. So that's only really appropriate for the binary tree. And of course, the other relationship is true. So the relationship, 9 has child 4 and child 12, but the reverse is true. So the left child and the right child. The reverse is true as well, that the 12 node has a parent node called 9. And the 4 node here has a parent called 9. So there's a child relationship, which is the links going down, and a parent relationship, which is really following the links back up. Okay. So once we have all of that notation kind of down pat, it's easier for us to see how the tree gets built. But let's talk about different types of trees. In particular, I want to kind of focus on a specific type of tree. So if we're talking about general trees, we're going to want to be able to insert new values into the tree. We're going to want to delete values from the tree. And we probably want to be able to see the root element, like just look at the root element. Because looking at the root element, we can then see what are the children of that root element, and we can work our way down towards the bottom. So the root function is sort of our starting point for looking for values, or maybe even looking for where should I insert a value, or where should I delete a value. So these operations are the minimal. But these aren't actually that useful because trees are so general that these functions aren't enough for us to actually use a tree. We're going to need to know specifically what kind of tree and how it works in order to figure out what all the operations are going to be. So let's consider only binary trees. So we've talked a little bit about this. Just to recap, a binary tree is a tree where the nodes can have up to 2 children. And again, we usually refer to the 2 children of a node in a binary tree as the left child and the right child. And we usually represent it graphically using the left side and the right side to match. Okay, and generally speaking, binary trees have 2 children. There are other types of binary trees in the world. There's all kinds of binary trees. I mentioned one kind of binary tree a few minutes ago was a heap, and a different kind of binary tree is called a binary search tree. They're both binary trees, but there are different rules for how to construct them. Whereas a heap typically has its smallest values up at the top, a binary search tree has its smallest values on the left-hand side. Okay, and one interesting thing about a binary search tree is that when I search for something in a binary search tree, sometimes called a BST for short, by the way, that BST, I start at the root and I work my way down to the bottom. If the tree is nice and balanced, then the amount of the height of the tree is about log base 2 of n. If you're not familiar with log base 2, log base 2 of n is some value. Let's say, for example, log base 2 of n is equal to k. Then I'm really asking 2 to what power is equal to n? Okay, so 2 to the k is equal to n. So what's k? So that's really what this log base 2 of n is. And log is kind of the opposite of the exponent. So exponent is a function that grows really rapidly. And actually log is a function that doesn't grow rapidly at all. And so if you drew a graph of the exponent operation, which 2 to the n, for example, and you can in fact do that if you want to. Go into Desmos graphing calculator, look up Desmos, D-E-S-M-O-S, click on their graphing calculator, and literally put 2 to the exponent n, like 2 caret n, and see what it looks like. It's a graph that grows really, really quickly. And then if you look at the graph of log base 2 of n, you'll see that it's a graph that starts to kind of level off. And in fact, it's a reflection of that same curve about the 45-degree line. And so this is a very efficient size for a binary tree, and that directly correlates to how efficient the searching is. Because if the height of the tree is generally quite small, then that means as I work my way from the top to the bottom, I only have to do a really small path from top to bottom. And then by the time I get to the bottom, I haven't looked at that many nodes. So it means that searching is very efficient. Because I don't need to check all the elements on the way down, I just need to follow one path from top to bottom. So the more balanced the tree is, the smaller the height, and the more efficient the searching is. So the trick to a binary search tree is to keep it balanced. And you'll see in the animations that not all of the binary search trees are balanced, so we might need some special procedures for that, which you'll learn about in future courses. But for now, we're just going to consider binary search trees which don't balance themselves. Okay, so we talked quite a bit about a binary search tree. Just to recap, they are ordered from left to right. The smallest elements are on the left and the largest elements are on the right. To be a bit more precise, for any node in a binary search tree, the node itself's value is going to be strictly greater than any value in the left child or any descendant of that left child. We use the term descendant to refer to the child or the child of the child or whatever. And so imagine I've got a node in my tree, and I look at the left child or any of the children of the left child. All of the values in that left child and all of its children, they're all smaller than the root node's value. And all of the values in the right, we call this the right subtree, which is basically the right child or any of the descendants of the right child. All of those values are greater than or equal to the root's value. And that's not just true for the root. It's true for every value, every single node in the tree. So we have this left to right property where the values in the leftmost position in the tree are the smallest values, and the values in the rightmost position of the tree are the largest values. And when we're searching this tree, we're going to use the binary search algorithm to do so, as we're going to see when I show you the animations. So let's talk about how we can implement a binary tree. And in so doing, we can also implement a binary search tree. Binary search tree only differs from a binary tree in that we have to maintain that ordering. And so, of course, I could simply do that. We could implement a heap binary tree or a binary search tree or any other kind of binary tree in these ways. So I'm talking about general ways to implement any binary tree. So first I might consider how to implement it using an array. You shouldn't be too surprised. We talked about how stacks can be implemented using an array, and queues can be implemented using an array. You can implement a binary tree using an array, and it's actually quite cool the way that it works. So first of all, we're going to have a root element, and the root element is always inserted in the first position of the array, or index 0. And for any element within the tree, including the root, its left child is found at position 2 times I plus 1, if there is a left child. And its right child is found at 2 times I plus 2. So we just use these formulas to figure out where things should be in the tree. And it works out really nicely such that we don't have any overlap of any of these nodes. So element i's children and element I plus 1's children don't overlap with one another at all. We can also go backwards. So we can find the parent node for any node. Obviously, there's no parent node for index 0 because index 0 is the root of the tree. That's the only node in the tree that doesn't have a parent node. But the parent can use this formula, I minus 1 divided by 2. But notice here that I'm using the Python syntax for integer division or floor division. So here, I minus 1, integer division 2. That means if there's any fractional part, we just throw away the fractional part. Anyway, we'll see this in action in the animations. You can also implement it using a linked structure. Not a linked list, because a linked list is very one-dimensional, but a linked structure. So what we can do is we can create nodes with the stack and the queue implementation using a linked list. We had a node that had a value and a next pointer. But with the binary tree, what we do is we have a value, and we have a pointer for the left node and a pointer for the right node. But otherwise, it's a really simple process. If we have a branch node, then the branch node is going to have one of its pointers pointing to a node on the left and one of its pointers pointing to a node on the right. It is possible that one of these is null if it doesn't have a left child or a right child. But leaf nodes aren't going to have a left child or a right child. They're going to have neither. So both of these pointers will be set to null in that case. So we can use both of these binary tree implementations for binary search trees, and in fact in the animations I'm going to use binary search trees exclusively for demonstrating how insertion and deletion and search work within that tree. Okay. The only thing is that insertion and deletion are obviously going to work a certain way for a binary search tree, because when I want to insert a value, I have to make sure that I maintain that ordering that we talked about, which is the binary search tree property, which is just saying for every node, the values on the left side, on the left subtree of that node, have to be smaller, and the values in the right subtree of that node have to be greater than or equal to. We have to make sure to maintain that when we insert and delete. So by deleting a value, we can't mess that property up. And by inserting that value, we have to insert it in the proper spot. So there is a specific spot in the tree where those values are going to have to go, such that they're between the smaller values and the larger values. Okay, so we'll specifically talk about this kind of insertion and deletion when I show you insertion deletion for binary trees, we'll just use binary search trees. Obviously, insertion deletion will be a little different in a different kind of binary tree, like a heap, but you can learn about how those insertions and deletions work when you learn about heaps later. All right, so binary search trees are a little bit more complicated to implement, but they're relatively simple to understand at a conceptual level. So here I've got some code that's going to test our tree by inserting 6 elements into it in kind of a random order, and then we're going to delete 2 of the elements so we can see how deletion works for certain special cases. So a tree is normally empty, so on the right-hand side there is a tree, but we don't happen to have any nodes, including we don't have a root node. So let's go through the first insertion. The first element that we want to insert is the 7. So we're going to create a new node, and that will become our root node. I'm going to show that up at the top of the tree. All right, the next thing we're going to need to do, that was pretty easy because we had nothing in the tree. But now that we want to insert the -3, we have to make sure that the -3 gets inserted in the proper place in the tree. In a binary search tree, as its name kind of implies, we're going to use something that's very similar to binary search in order to determine where the element -3 should end up in our tree. So in this case, just like we do in binary search, we look in the middle element in binary search, and if the element we're trying to insert is less than that element, we want to insert to the left side. And if it's greater than or equal to, we want to insert it into the right side. -3 is less than 7. So what we're going to do is we're going to insert a new node as a left child of the 7 node. So nodes in a binary tree are going to have left children and right children. That's why they're called binary trees. Two children. So you can see that gets added to the left-hand side. Now again, this will let us practice with our binary search tree search. And now we're going to insert a 1. So first we look, starting at the root node. Is a 1 less than a 7? Yes, it is. So what we want to do is we want to insert it on the left-hand side. Well, there's already a value on the left-hand side, so let's follow that link. Now we're going to go down to -3, and we're going to ask the same question. Is 1 less than -3? In this case, it's not. So 1 is greater than or equal to -3. So we're going to add the 1 as a right child of the -3 node. So we'll create a new node, and we'll create a pointer from the right child to the 1 node from the -3 node. Okay, now we want to insert a 9. Again, let's practice our binary search tree insert. For the 9, I'm going to look at the 7, starting at the root. You always start at the root. Is this 9 less than 7? No, it's not. So I'm not going to insert it on the left-hand side. The 9 is greater than or equal to the 7. And so I'm going to insert it on the right-hand side. Now, 7 doesn't have a right child right now, so that's perfect. We'll insert the 9 right there as the right child of the 7. All right, so again, let's insert the 11 now. So first what we're going to do is we're going to examine the 7. Is the 11 less than a 7? No. So we're not going to add it to the left side. The 11 is greater than or equal to the 7, so we're going to add it to the right side. Unfortunately, 7 already has a right child, so we're going to follow that right link to the 9 node, and we're going to ask the same question again. So is the 11 less than 9? Nope. So we're not going to add it as a left child of the 9. The 11 is greater than or equal to the 9, so we're going to add it as a right child of the 9. 9 doesn't have a right child, so that fits perfectly. So we can stop as soon as we find a place where the 11 fits. All right, moving on to the 8, one more chance for us to practice. 8 is not less than 7, so we don't traverse the left link. It's greater than or equal to the 7, so we traverse the right link. We go from the 7 to the 9. Then we ask the question again, is 8 less than 9? In this case, yes it is. So we want to add the 8 to the left of the 9 within this tree. And since 9 doesn't have a left child, that works out perfectly. We can add the 8 as a left child of the 9. So we're going to create a new node and add a left child pointer from the 9 to that 8 node. Now let's see what happens when we delete. So first we're going to try to delete the 11, which as you're going to see is a very easy thing to delete because 11 doesn't have any children, and as a result, it kind of just comes right out without any side effects. And so we can literally just delete the 11 without doing anything special. But let's look at another example where that's not the case. So here we have a 7. We're trying to delete the 7. Well, the 7 has 2 children. And so we need to make sure that this is still a tree when we're done. And if we delete the 7, not only are we deleting the parent of 2 nodes, but we're also deleting the very root of our tree, which is the starting point for all of our searches, as we've seen. And so as a result, we need to be very careful and make sure that we have a root node when we're finished. So we're deleting the 7, so we need a replacement for the 7. And because the binary search tree has a specific ordering where all the smaller values are on the left-hand side and all the larger values or equal values are on the right-hand side, we need to make sure that that ordering is preserved. So what we need to do is choose the value that is the closest to the 7. And this is actually a bit complicated because the values that 7 has direct access to, its left child and its right child, are -3 and 9, and these are not the closest values to the 7. What we want is something close to the middle. So we either want the 1 on the left-hand side, because that, of all the values that are smaller than the 7, it's the largest one. Okay, so it's the closest value to the 7 that's smaller than the 7, the 1 is. And similarly, if we go down the right-hand path, the 8 is the closest value because of all the values that are greater than or equal to the 7, it's the smallest one. So we want the value that's as close to the 7 as possible. Now in this case, numerically, the 8 is a lot closer to the 7 than the 1, but from the point of view of somebody who's implementing a binary search tree, they're both equally good choices. We can replace the 7 with a 1, or we can replace the 7 with an 8. Doesn't really matter. Okay? The rule is we either replace the rightmost node that's in the left subtree, so the left subtree is the -3 and the 1 part of the tree, and the rightmost node in that part of the tree is the 1, or we replace it with the leftmost node that's in the right subtree. So the right subtree is the 8 and 9 nodes, and the leftmost one in that subtree is 8, and so we can replace it with the 8 or the 1. I'm going to choose to replace it with the 8, but just so you know, that's not a better choice than the 1. The 1 would work out just as well. Okay, so now we have deleted those 2 values. So now what I want you to do is to think about what would happen if I wanted to delete the -3. So if I wanted to delete the -3, I don't have any animation for this, but just as a thought exercise for you, what would happen if I wanted to delete the -3? I would need to promote a node in its place because the 1 would be left dangling if its parent was deleted. So I need to make sure that I take care of that child node. I need to promote one of the nodes from below the -3, and I want to find the closest value to the -3 that I can to replace it. Now in this case, there's only one choice. I would replace the -3 with the 1. Okay, so the 1 would get promoted up 1 level, and it would take the place of the -3. Anyway, it's good to think about these things to get some practice for when you're ready to implement it. Now, just to give us some extra practice, what I'm going to do is show you how an entire binary search tree would be built, one element at a time. The styling is a little different because I created this animation a few years ago. But anyway, so in this case, we want to insert a 3 into this tree, and it's not equal to the 7. It's less than the 7. So that's going to tell us we want to insert it on the left side. So we create a new node for the 3, and we make the left child that 3. The next value we want to insert is a 10. And so what we're going to do in this case is I'm going to check to see if it's equal to the 7. If it's equal to the 7, we might decide, do we want multiple 7s in our tree? Do we allow that? If we do, we might put the equal ones on the right-hand side or whatever, or we might just not insert it if we don't want duplicates. So that's why it's going through a step where it's checking to see if it's equal. Now I'm checking to see if 10 is less than 7, and it's not. So obviously 10 is greater than 7, so we're going to insert it to the right-hand side. So we're going to create a new 10 node. We're going to point 7's right child pointer to it. Okay, and now we're going to ask, okay, now we want to insert a 1. So is a 1 equal to the 7? Nope, it's less than. So we're going to traverse this link to the 3 node. And now we're going to ask the same questions about the 3 node. So is the 1 equal to 3? No, it's not. Is the 1 less than the 3? Yes, it is. So we're going to add the 1 as a left child of the 3 node. Next value I'm going to try to insert is a 5. Is a 5 equal to the 7? No, it's not. A 5 is less than the 7, so we're going to follow the left link Now for the 3, is that equal to 5? No. Is it less than? Is the 5 less than the 3? Nope. The 5 is greater than the 3, so we add it to a right child. Since there is no right child, the 5 can be the right child of the 3. Next value we want to insert is a 9. So that's not equal. So again, we start at the root every time. Is the 9 less than the 7? Nope, so we don't add it to the left side. It's greater than, so we're going to add it to the right-hand side. There's already a right node, so we go down to that right node and we ask the same questions again. So we have a 10. 9 is not equal to the 10, but it is less than the 10. So we're going to insert it as a left child of the 10 node. One more value to insert, 19. So is 19 equal to the 7? Nope. Is it less than the 7? Nope, definitely not. So we don't add it to the left side. So we traverse the right link because it's greater than the value of the 7. So now we're looking at the 10 node. Is 19 equal to that 10? No. Is it less than that 10? No. If it was, we would go left and follow that link to the 9. But it's not, so we want to insert it on the right-hand side. So we create a new node for the 19, and we add it as a right child. Okay, we'll do one more. And in this case, I want to insert a 4. 4 is less than the 7, so we go left. And then we check to see if the 4 is equal to the 3. It's not. So it's not less than the 3. It's greater than the 3. So we're going to go right to the 5 node. And then looking at the 5, again, the 4 and 5 aren't the same. So the 4 is less than the 5. So we're going to add it as a left child of the 5. Okay, and that's the basic idea of doing insertion and practicing with the binary search tree. While you're inserting things into a binary search tree, you use basically something that is binary search. So let's do something very similar, but in this case, what we're going to do is we're going to delete all the elements of a tree. That'll give us a chance to see a couple of different cases where we're going to do it. I'm also going to show you that the binary search process is also present when we're deleting from the tree because we have to find the node before we can delete it. So the first thing we're going to do is we want to delete the 5. So is that 5 the 7? Nope. The 5 is less than the 7, so we're going to go left. Now we're looking at the 3. The 3 is not the 5. And the 5 is not less than the 3, so we don't want to go left. We want to go right. Okay, so 5 is greater than the 3, so we go to the right. And now we're going to check, well, is that 5 the value I'm looking for? Yes, actually it is. So now I can delete the value. Now here I can look at the node and see that it has no left child and no right child. So there aren't going to be any side effects if I just delete the 5. All I really need to do is go up to the 3 node and delete its right child pointer and delete the actual 5 node, and I'm done. So deleting leaf nodes in a tree is very easy to do. Okay, there are no side effects. And we'll see a couple of other examples though. All right, let's see what happens if we want to delete the 7. Well, 7 is a tricky one to delete, as we've seen. So I have to choose, and I'm just going to write my algorithm one way or the other way. It doesn't really matter which way. But I can either choose the greater of all the elements on the left-hand side. Remember, all the elements on the left-hand side are all smaller than the 7. So if I pick the biggest one of all those values and promote it to the new replacement value for the 7, then it will maintain the ordering left to right. And I can also, of all the values from the right-hand side, or the right child, or the right subtree of the 7, those are all values that are greater than or equal to the 7. So if I pick the smallest one of those, or the one that's most left, then I will pick the value that's the closest and best replacement for the 7. So in this case, I've got two choices. I can promote the 3, so the 3 is the largest of all the smaller values than 7. Or I could pick the 9. The 9 is the smallest of all the larger values than 7. Those are two perfectly valid choices, and I could choose either one. I believe that I promote the 9 here, just to be consistent. Oh no, I'm sorry, I remembered wrong. I promote the 3. And with the 3 comes its left child, which is the 1. So the 1 gets shifted up to the top. All right, so let's delete another value. Again, they're both equally correct choices. So delete the 9. We're first going to check to see if the root node is a 9. It's not. And 9 is not less than the root node value. It's greater, so we're going to go to the right. And we're going to go to the 10 node. Now we're going to check, well, is that node a 9? No, it's not. So is the 9 less than its value? Yes, it is. So we're going to go to the left, and that's how we get to this value. We check to see if it's the correct value, and now we know this is the node that I want to delete. I want to delete the 9. And so I can look at the left and right children. Again, this is a leaf node, so we can just delete it without any consequences. There's no need for any promotion or replacement, so we can just delete it. Okay. Next, let's delete the 19. So the 19 is not equal to the 3, so it's not the root node that we want to delete. And it's not to the left of the root node because 19 is not less than that 3. 19 is greater, so we go to the right. So next thing we're going to examine the 10. And the 10 is not equal to the 19 that we want to delete. And the 19 is not less than that 10, so we don't want to go to the left. And we do want to go to the right. Now I just want to point out one thing real quick here. Is what if I was looking to delete the 19 or delete a number like a 9 in this case, and 9 is actually less than 10, so I would want to delete the left child of the 10. But in this case right now, there isn't currently a 9 node that's a left child of the 10. The 10 doesn't have a left child. That could happen, and basically what you're trying to do is you're trying to handle the situation when the user's trying to delete an element from the tree that's not in the tree. And what you should do in that case is really depends on what you want to do, because maybe you want to tell the user you're trying to delete an element that isn't actually in the tree. Maybe you want to have some kind of an error message indicating that. Or you could just quietly not delete anything because there really is no matching value to delete. What you do may depend on how you plan on using your tree. So that's just a hypothetical little interjection. I'm sorry about that. So we find the 19. It's again a leaf node, so no problem. We can delete it. And I got to be careful, make sure that I delete the right pointer of the 10 node that pointed to that 19 node. But anyway, let's keep on deleting. So the next one I want to delete eventually. Oh, oops, sorry. This is actually the end of this example. Sorry, I didn't delete them all. Hypothetically, if I wanted to delete the 3 in this case, for example, that's the only one that's challenging here. I could delete the 1 and the 10 because they're both leaf nodes really easily. If I want to delete the 3, I could promote the 1 as the new root of the tree, and then the 1's right child would be the 10. Or I could promote the 10 to the new root of the tree, and the 10's left child would be the 1. All I'm doing is basically moving this 1 into the position of the 3, and it's going to absorb the remaining children of that 3 node, because the 3 node is going to be deleted. It can't obviously have any pointers to its children anymore. I need to have a node that still points to those children, so those children are still accessible. And it's either the smallest of all the values to the right, which is the 10, or the largest of all the values to the left, which is the 1, and they're both equally good choices. Okay, so now let's consider the ways that we can implement a binary search tree. So we're going to implement the binary search tree, not too surprisingly, using an array and also using a linked structure, similar to a linked list. It may actually be surprising that we're implementing a tree as an array, because inherently a tree is sort of a two-dimensional looking structure, and an array is very one-dimensional, very flat. But with some math, and you can see the functions implemented in Python down at the bottom, it is possible for us to represent a binary tree specifically using an array. Okay? Other types of trees are a bit more challenging, but binary trees are pretty easy to implement in an array. So I've got an empty array over on the right-hand side. Of course, we're going to add some indices to that, but we've got the exact same code on the left-hand side that we did with the conceptual example at the beginning. And we're just going to use these formulas down here to figure out where everything should go. Except at the beginning, when we add the 7, we're going to add it to the root node. The root node is always going to be inserted in the first position of the array. So that's going to be a very easy decision. So let's walk through this code. So first, we want to insert the 7. So we'll do it conceptually in the middle. I'll show you what the tree actually is supposed to look like. But you can see that the 7 just gets added to index 0 in the array. So that's really easy. But now, again, just like we did with the other examples, we're going to try to figure out where the -3 should go. The -3 needs to be inserted as a left child of the 7 because it's smaller than the 7. And if we want to figure out where the left child is, we've got this function down at the bottom middle here called left. And what we do is we pass it the index of the parent node, and this function will return the index of where the left child should be. And so if we actually apply the index of the 7 to this function, the index of the 7 is a 0. And so we're going to set index equal to 0. So left is going to return 2 times 0 plus 1, which is going to give us 0 plus 1, or 1. So the proper place to insert this -3 is going to be at index 1. So let's see that. So you can ignore, the tree in the middle is just a reminder of what the actual tree looks like, but just to keep things really concrete, we've got the actual array on the right side. All right, the next one we're going to try to insert is a 1. So where should the 1 go? Well, again, using binary search, the 1 is less than the 7, so it should definitely be left of the 7, so we're going to follow that left link. And the 1 is greater than or equal to the -3, so it should be the right child of the -3. So how do we figure out the right child? Well, we've got this function down at the bottom right of the screen called right, which says, given a parent index, the right child is at 2 times that index plus 2. So because I want to insert this 1 as a right child of the -3 node, I first have to figure out -3's index. -3's index is at 1. Okay, so I put 1 into this right function. 2 times 1 plus 2 gives me 2 plus 2, which is 4. So I'm going to insert this 1 at index 4. And that's a little weird. We've got some empty spaces in our array, but that's fine, actually. And the empty spaces that are there at index 2 and 3 there, those are for the other children. So for example, space 2 is the right child of the 7. So you can see we don't have a right child of the 7, and that should actually appear first. And space 3, index 3 in this array, should be the left child of the -3, which we don't have yet. All right, so let's keep on inserting. So next we're going to do is insert a 9. So the 9 should actually be on the right-hand side of the 7. And 7 doesn't currently have a right child, so let's actually add it as a right child of the 7. So taking the 7's index, 0, and putting it into the right function down at the bottom, we're going to get 2 times 0 plus 2, or 0 plus 2. So that means that the 9 should be inserted at index 2, because it's going to be the right child of the 7. That's pretty easy. Next thing, we're going to insert 11. So 11 is greater than or equal to the 7, so it should be on the right-hand side of the 7. There's already a right node of the 7, so let's follow that link to the 9. The 11 should be on the right-hand side of the 9 because it's greater than or equal to the 9. And 9 doesn't have a right child. So let's insert the 11 as a right child of the 9. The 9 is at index 2, so let's put that index into the right function. 2 times 2 plus 2 is going to give us 4 plus 2, or 6. So I'm going to insert the 11 at index 6 in the array. There we go. Next, let's insert an 8, the final insertion. So where does the 8 go? Well, the 8 is greater than the 7, so again, starting at the root, it's greater than the 7, so we go right. And then we look at the 9. The 8 is less than the 9, so we want to go left, but 9 doesn't have a left child, so let's add the 8 as a left child of the 9. So the 9 is at index 2. So putting the 2 index into the left function is 2 times 2 plus 1. That's going to give me 4 plus 1, or 5. Let's insert the 8 at index 5. Okay, there we go. So now I just want to note something now that we're seeing how this gets inserted into the tree. If you just read the values kind of row by row through the conceptual tree, you'll see that they actually are in the same order that they are in the array. So the top row only has a 7, and the 7 is the first element in the array. The second row in the tree is -3, 9. You can see those are the next 2 elements in the array. The bottom row has a missing spot, right? And so whatever that is, there's a blank space, then there's a 1, then an 8, then 11. And you'll see that at index 3, 4, 5, and 6 are a blank space, 1, 8, and 11. And guess what index 7 is for? Well, it's actually the left child of the blank space at index 3. So you can keep adding more array elements, more array spaces here, and that'll give you more flexibility for adding larger and larger trees. All right, so let's watch what a delete is. So the simple kind of delete is when we delete a leaf node. So let's try that first. We're trying to delete 11. So again, we first try to find the 11. So 11 is greater than 7, so we go right. And then 11 is greater than 9, so we go right. And there's the 11. So we found the 11. It's at index 6. And we want to delete it now. And it doesn't have a left or a right child. We could check to see if the table is empty, the array is empty. By looking at the indexes, by passing 11's index 6 into the right and left function and see if those indexes have any values. They won't in this case. Maybe there are some empty spaces, but there aren't any values there. So we can literally just delete the 11. Nothing too magical that we have to do. We just literally delete the value from the array. Okay. So the next thing we're going to do is try to delete the 7, which is obviously a more complicated thing to do. So we're going to have to choose whether we want to promote a value from the left side of the 7. So the 7's at the top. It's the root node. So we're going to need a replacement root node. But even if it's not the root node, if it has any children at all, we need to make sure and find a replacement node. So we're either going to find the rightmost node on the left side of the 7, which would be 1 in this case, or we're going to promote the leftmost node on the right side of the 7, which would be 8 in this case. Now I chose 8, but it doesn't really matter. Both 1 and 8 are both correct choices. And admittedly 8 is numerically closer, but that doesn't actually matter. So hold on a quick second. Let's see what actually happened in the code. So you can see the 8 was at index 5. And now when I replace the 7, I'm going to delete the 7 from index 0. And I'm going to move the 8 from index 5 to index 0. So the 8 actually shifts up. Right here. It went back a little too far. So the 8 actually moves up into the 0 position, overwriting the old value. And the extra copy of the 8 at index 5 is no longer there. So the other way to implement a tree, well actually there are other ways to implement a tree, but the other way that we're going to talk about is to use a linked structure. So not exactly the same thing as a linked list. A linked list is very one-dimensional, and although you can use a one-dimensional structure, an array, to represent a tree, it isn't particularly convenient, and it's not taking advantage of the whole idea of pointers like a linked structure could. So what we're going to do instead is we're going to do something that's very similar to a linked list, but instead of just having each node linked to one other element, why don't we just create a kind of node that has a left and a right pointer, and the left pointer will go to the left child, and the right pointer will go to the right child. And that will actually make it much easier for us to implement this tree. So I'm going to represent graphically a little bit differently. So we're going to insert the 7. That gets inserted at the root of the tree. So we'll just create a new node. We'll probably have a pointer that says the root is here, and it points to the 7 node. You'll see that we have little boxes to the left and the right. These are where the pointers to the left and the right child are respectively. Right now there's nothing in them, indicating that these are set to null because there's no left child and no right child. So now we want to insert the -3. Again, binary search tree rules. We're going to want to insert this on the left-hand side. So let's create a new node with a -3 with left and right pointers that are set to null, and we'll overwrite the left pointer of 7 to point to that new 3 node because the -3 rather, is less than that 7. Now we want to insert the 1, so we're going to look at the 7. We're going to look at the 7. The 1 is less than the 7, so we're going to go down to the 3 node. The 1 is greater than or equal to the 3, so we're going to add it as a right child of the 3. So we're going to create a new node which has a 1, and a left and right child are both going to be set to null. And we're going to point the right pointer of the -3 to this new 1 node. I'm going to position it kind of down there so that we can see where it belongs. Next, we'll insert the 9. Just want to point out something interesting here. This isn't specific to the link structure implementation, but you'll notice that after inserting these 3 values, you'll see that our tree is very lopsided. We have a lot of stuff on the left side, and we have nothing left on the right. And this is, in fact, one of the flaws of this simple implementation of the binary search tree. Techniques which try to keep the tree balanced, which makes it more efficient for searching, will be discussed in future courses. So you'll learn about AVL trees and red-black trees and things like that in the future. All right. So now we want to insert the 9. The 9 is greater than the 7, so we're going to add it to the right-hand side of the 7. And again, that happens just by actually setting the right pointer of the 7 node to point to the new 9 node that we just created. And similarly for the 11, we're going to go to the right of the 7, to the right of the 9, and since to the right of the 9 there's nothing, we can add the 11 as a new right child of the 9. So we'll create a new node, we'll point to the right pointer to that node. When we insert the 8, it's very similar. The 8 goes to the right of the 7 and to the left of the 9, so we add it as a left child of the 9. Similarly, when we delete, all we do is we find our way to the 11 node. So we're looking for 11, which is greater than 7, so we go to the right. 11 is greater than 9, so we go to the right. 11 is equal to 11, so we found the node. We can just delete it because there's no left child or right child. Its left and right pointers are both null. So we can delete it because it's a leaf node. And when we delete the 7, we'll find that right away. So 7 is equal to 7, that's the root node. And so we need a replacement for the root node. So I'm going to make the same choice that I did in the other videos. I'm just going to promote the 8. So in this case, the 8 is the smallest of all the values that are larger than 7. But 1 would also work equally well. And so what I'm going to do is I'm going to delete 7. And then 8 is going to get promoted, and its left and right pointers are just going to be set to be the same as the left pointers of the 7 node. So right now, the left pointer of 7 points to the -3 node, and the right pointer of 7 points to the 9 node. I'm going to make sure that the 8 left and right pointers point the same way when we're done. Okay. I got a little graphical glitch there. Sorry, the little boxes didn't go up with it. But anyway, I'm sure you get the idea. All right, so there's how we implement it. It's just a matter of manipulating pointers. And you just, like all pointers, you just need to make sure that you are actually not using a pointer that has an invalid value, like set to null or trying to use it or whatever, the usual pointer things that you can run into. All right, so thanks, everybody. Okay, so that's it. It's not meant to be a complete discussion of data structures. There's usually a course or even 2 courses that deal with data structures and algorithms. So both of these 2 topics were meant as just kind of a brief introduction, and then you'll take a couple of courses later on where you learn a combination of data structures and algorithms. Now, even those courses are often called data structures and algorithms separately. Usually the data structures course introduces data structures and the algorithms that you need to write in order to work with those data structures, such as how do you insert into a binary tree. So it's both data structures and algorithms, really. And when you take a course on algorithms, you're going to learn some more advanced algorithms, but oftentimes those algorithms use data structures. So they might use a priority queue or they might use a stack. So these 2 things are interwoven, and you're always going to learn data structures and algorithms together. So even in your future courses, that's true. So that's why I tried to make sure these 2 topics were close together so we could get a pretty good idea of how they intermingle with each other. All right, so thanks, and I'll see you next time.